Hello students, let us resume our teaching in carbohydrates. We are studying monosaccharides, and in monosaccharides we are just discussing the structures of optical isomers of trioses, tetroses, pentoses and hexoses. We have already covered the isomers of trioses, tetroses and pentoses. We have already seen that trioses have one asymmetric carbon atom and number of isomers. It has two number of isomers, aldotriose. Now ketotriose has no asymmetric carbon atom, so no isomers. Then aldotetrose has two asymmetric carbon atoms. It has two asymmetric carbon atoms and therefore it will have four number of isomers. And who are they? Now they will be two D isomers and two L isomers. And who are these two? They are erythrose and threose. Then when we go for ketotetrose, we will have one asymmetric carbon atom. So there will be two optical isomers and these are one D and one L. So that is erythrulose. And when we come to aldopentose, there are three asymmetric carbon atom and therefore there will be 8 numbers of optical isomers, out of which there will be 4 D isomers and 4 L isomers. And these isomers are ribose, both D ribose as well as L ribose. Then arabinose, xylose and lyxose. Then ketopentose, there are two asymmetric carbon atom, so there will be 4 isomers and these are 2D and 2L isomers and they are ribulose and xylulose. So this much we have already gone through. We have seen structure of each of these molecules. We have seen the structure of each of these molecules. I have drawn the structure of all D isomers and I have told you how we will get the structure of L isomers by simply taking the mirror image of those molecules. Then we will go for the hexoses. We will go for the hexoses. When we come to the hexoses, first we will discuss aldohexose, then we will discuss the ketohexose. Now, when it is aldohexose, there will be 4 asymmetric carbon atoms. There will be 4 asymmetric carbon atoms. Therefore, number of isomer will be 2 to the power 4, that is 16. 16 isomers, and these 16 are 8 D isomers and 8 L isomers. There will be 8 D isomers and 8 L isomers. Now, who are these isomers? Let us see one after another, that is allose, ultrose, then we will have the glucose, mannose, then galactose, and there will be idose and talose. These 8 isomers are there, and this is very famous. We are very much acquainted with this one, that is glucose, and also this is mannose, and of course the galactose. These 3 out of these 8, these 3 are very important. We will now see the structure of each of them. We will see the structure of each of them. Let us first begin with allose. Now, if you remember, these are hexose, so there will be 6 carbon atoms. Last one is always CH2OH. First one is always CHO. And since we are going to deal with the structure of the D isomer, so in the D isomer, furthest asymmetric carbon atom, that is the 5th one, furthest asymmetric carbon atom will have a structure like this. So, this is the standard format of all these aldohexoses in their D configuration. When we take the D configuration, this will be their structures. So, this is the standard one. Now, after taking care of this last asymmetric carbon atom, we will take care of these 3 asymmetric carbon atoms. Let us see how their structure changes. Now, first when we go for the allose, in case of allose, remember, in case of allose, all these hydrogen will be on the left side. These are on the right side. So, now this becomes your allose. This becomes your allose. Next one is your ultrose, D-ultrose. In case of D-ultrose, in this will simply undergo change. I am just showing you the structure of D-ultrose, showing you the structure of D-ultrose. So, this is now your D-ultrose. This one is your D-ultrose. We find this change in the carbon atom number 2, hydroxyl group on the left side and hydrogen on the right side. Next is your glucose. When we come to the glucose, let us make it normal again, OH, then this is H. So, when it is glucose, so this allose is over, ultrose is over. When we come to glucose, this 3rd carbon atom will have this hydroxyl group on the left side. So, this becomes your glucose. You just see the position of the hydroxyl group and hydrogen are getting changed, and each change produces a new isomer, new optical isomer or stereoisomer. So, this is your glucose. Then we go for the mannose. In case of mannose, both 2 and 3 will have the hydroxyl group on the right side. sorry, in the left side, hydroxyl group, and this is the hydrogen. So this is the structure of mannose. This one is the structure of mannose. You will find here in the second and third, this is our carbon atom number 1, this is 2, this is 3, this is 4, this is 5, and this is 6th. So in the second and third, hydroxyl group are on the left side, and right side there will be the hydrogen. So this is your mannose, and after mannose there is the glucose. When it is glucose, we will find, again we return to the normal one first. This will be H, OH, H, OH. Well, this is our normal allose structure. This is the structure of the allose. Now here what happens, in the fourth carbon atom, hydroxyl group will be on the left side. So now it becomes glucose, G-U-L-O-S-E. This is your glucose. Then next one is idose. Next one is idose. In case of idose, we will have it here in the second and in the fourth. The hydroxyl group will be on the left side in the carbon atom number 2 and in the carbon atom number 4. Then it becomes your idose. Well, then we go for the galactose. In case of galactose, we will find this to be normal, and here this is like this. In the third carbon atom and in the fourth carbon atom, we will find hydroxyl group will be on the left side in both the cases. Hydroxyl group is on the left side, whereas second and fifth we are not considering, because fifth is reserved for being D or L. In case of D, hydroxyl group is on the right side. Now, next one is so this is your galactose. This is the structure of galactose. Mark it, it is at the third and fourth carbon atom. Hydroxyl group is on the left side. Then last one is the talose, where we will find all of them are on the left side. In carbon atom number 2, 3 and 4, it will be on the left side. Carbon atom number 2, 3 and 4, the hydroxyl groups are on the left side. So this is what the aldohexoses, we have seen the aldohexoses and their structures, and to get any L configuration, of these allose, altrose, then glucose, mannose, glucose, galactose, idose, talose, all of these things we can get by simply taking their respective mirror images. Will give their L configurations. Then we will go for the after the aldohexose, we go for the ketohexoses. When it is ketohexose, the number of asymmetric carbon atom is 3. So there will be 8 isomers, which will be 4 D isomers and 4 L isomers. We will have 4 D isomers and 4 L isomers. These D isomers are psychose, then fructose, sorbose and tagatose. These 4 are there. These are psychose, sorbose and tagatose. Out of them, this is very, very common. Fructose is very, very common, and fructose has a very good qualifier. It is the sweetest among all monosaccharides. Fructose is the sweetest among all monosaccharides, and as the name suggests, it is plentifully present in fruits, plentifully present in fruits. So, that is why its name is also fructose. Now, let us draw its structure. So, standard structure first we will draw, that is first carbon atom is CH2OH because it is a ketone. So, second carbon atom there will be ketone group, then third, fourth and fifth carbon atom we will have, because it is a D isomer, hydroxyl group will be on the right side in the fifth one. So, this is the furthest, fifth one is the furthest asymmetric carbon atom, 1, 2, 3, 4, 5 and 6. So, fifth carbon atom is the furthest asymmetric carbon atom. So, it will have the hydroxyl group on the right side in case of the D isomers. So, now we have actually two more asymmetric carbon atoms, So, around it the configuration of the hydroxyl group and hydrogen will be maximum 4 positions, maximum there will be 4 kinds. First of all, in case of psychose, it will be HCOH and HCOH. This is the structure of the psychose. All these two, in the third and fourth carbon atom, hydroxyl group will be on the right side. Then when it is the fructose, it is on the fructose case, we will find this is your fructose. In the third carbon atom, hydroxyl group will be on the left side. Hydroxyl group will be on the left side and this will be on the, hydrogen will be on the right side. So, this is your fructose. Now, if you remember, in case of aldohexose, hydroxyl group remains on the right side. In case of glucose. It was on the left side, third carbon atom. Next is sorbose. In case of sorbose, so this will be normal H, this will be HO, then here it will be HOCH. So, this is your sorbose. This is the sorbose. We will find in the fourth carbon atom, hydroxyl group is on the left side. In the fourth carbon atom, hydroxyl group will be on the left side. And when it is the tagatose, we will have both the hydroxyl group will be on the left side. So, this is the tagatose. So, these are the all available ketohexoses. So, now we will go for another interesting aspect of the structure of pentoses and hexoses. Another important aspect of pentoses and hexoses. Now, what happens interestingly, these aldopentoses can remain in ring form. We have already seen this structure. Say I am just drawing the structure of ribose. I am drawing the structure of D-ribose. Well, it is an aldopentose. D-ribose is an aldopentose. So, I will have C O well, so it can remain in a ring form. It can remain in ring form. Here what happens, this oxygen will interact with this hydroxyl group. A ketone and an alcohol, a ketone and ketone, this is the aldehyde. An aldehyde and an alcohol will react. Aldehyde and alcohol will react. Aldehyde will become alcohol and alcohol will become ether. So, this is the aldehyde group, and this is the alcohol group. Now, this aldehyde group will change to an alcohol group. Alcohol group means this double bond O will become OH, and this alcohol group, that is this OH, will become ether group. So, this double bond O, this is the aldehyde group, will become the alcohol group, and this alcohol group, which is at the fourth carbon atom, will become the ether group. We will see how it is happening. So, according to just when we look at that, so it will be single bonded, and we will have this hydrogen, mark it, this hydrogen will go here. Okay, this hydrogen will go there. So, let us erase here and put it here. Mark it step by step. So, now this becomes alcohol. This, it was double bond O, now it becomes single bond OH group. Now, this is being converted to ether now. It was an alcohol, now it is being converted to ether. So, this bond, it will make a bond with this one. This oxygen will make a bond with this hydroxyl group. So, this was an alcohol, now this will become an ether. How we will write it? This is what? So, we can rewrite it. In a ring form, we can rewrite it. How we will rewrite it? Just remember, this is the carbon atom number 1, this is 2, this is 3, this is 4, and this is 5. So, we will find this fourth carbon atom and first carbon atoms are joined with an ether linkage. This is ether group. So, we will put the ether group here, then we put carbon atom number, this is 1, carbon atom number 1, and this is carbon atom number 4. This is 1 and this is 4 are joined through this oxygen. Then 1 is joined to 2, this is carbon atom number 2, then 2 is joined with 3, then 3 is joined with 4. So, these are 1, 2, 3, 4, and fifth carbon atom is joined to 4. So, this is fifth carbon atom. Fifth carbon atom, it is CH2OH, fifth carbon atom. So, we put it here CH2OH. Then, third carbon atom, it is HCOH. So, what we will put here? We will put here H and here OH. Remember, whatsoever here, all these hydroxyl groups which are on the right side, we will put them on the bottom of this ring. So, in the second position, HCOH, we will put the H here and OH here. And in the first one, we will put H here, OH here. I will come to this point once again, I will come later on. Just see, and in the fourth carbon atom, there is one hydrogen, this one. Fourth carbon atom, there is one hydrogen, so we will put it hydrogen here. So you just check whether it is supposed to be C5H10 and O5. So count the oxygens, 1, 2, 3, 4, 5 is done. Hydrogen 10, 1, 2, 3, 4, 5, 6, 7, 2, 9 plus 1, 10 and C5, 1, 2, 3, 4, 5 all are there. So this is this structure what we have done when it becomes the ring form, we now call it is D-ribofuranose. This ring form is called the furan form. This ring form of the ribose is called the furan form, and now we can call it ribofuranose. Mark it, ribo, then furan, this is furan, that it is a ring form, and ose. Means ribose is there, just we have inserted the term furan here. So now some interesting features about this, let me tell you. Now first about the structure. The structure which we are drawing like this, it is called Fischer projection. This is called Fischer projection. The way we write, the manner in which we write the structure of this is called Fischer projection formula. And now the way we are writing it here, it is called Haworth projection formula. It is called Haworth projection. When we think of Haworth projection, there is certain interesting thing about it, just let me tell you. So there is a ring, there is a ring. This is the ring. Here it is carbon atom number 1, here it is carbon atom number 2, here it is 3, here it is 4 and here it is 5. This is the 5th carbon atom. So when we draw this ring, this plane of this ring is perpendicular to the plane of drawing, that is the blackboard. I am drawing here in the blackboard. So you can just think that this is the ring. So this plane of the ring is perpendicular to the plane of blackboard. So you can imagine that this carbon atom number 1 and 4, carbon atom number 1 and 4 are on the blackboard, whereas this C5 and O, they are behind the blackboard. The oxygen is behind the blackboard and 2 and 3 are projecting out of the blackboard. Carbon atom number 2 and 3 are projecting out of the blackboard. And in order to denote it, what we do, we shade it. We shade it bold like this. Always it is not necessary because it is difficult to draw it always in the exam like this, but once we can show it that it is supposed to be like this. So what it indicates, this shaded portion is towards the viewer who is seeing this structure, and this plane structure are behind this plane of drawing where we are drawing it. Then there will be the substituents. Here is the OH group and here is the hydrogen. Here it is the hydroxyl group, here is the hydrogen, here is the hydrogen. So here it is hydrogen and okay. So now all these substituents, they are always perpendicular to the plane of the ring. They are, again mark it, they are perpendicular to the plane of ring. So what happens, in other word we can say that they are actually parallel to the drawing of the drawing plane. Where we are drawing this structure, they are parallel to them. So we have to imagine it like this. If this is the plane of the drawing, this hydrogen and hydroxyl are like this. Here is the hydrogen and here is the hydroxyl group. Here is the hydrogen, here is the hydroxyl group. They are present like that. So, this structure is called the Haworth projection formula, and we have some interesting feature about this carbon atom number 1, which I will just discuss after some time.